Today's topic is on thermal properties of matter. All right. So we'll be mostly talking about matter. In this case, will not be restricted to gases. Only the previous topic, when we were looking at gas laws, obviously from the word gas, we were restricting ourselves from gases. How gases change, how the volume of a gas changes when temperature changes, how the pressure of a gas changes when volume or temperature changes, and stuff like that. But today we just want to look at the thermal properties of matter. Here we are not so much concerned about how much volume, how much pressure, how much what. We just want to look at heat, heat, and heat. But of course, we also talk about thermal. Here, as you will see, I'm sure you will realize that there would be a difference between what we call thermal energy and heat energy. So you will definitely see that in a while. So when we talk about the concept of heat, all right, I'm sure you guys have heard of heat before. And today we would like to just analyze the scientific sense or scientific feel in terms of the physical science feel of heat. So heat energy in just a simple definition would be like heat is the energy transferred from a warm body to a cold body. All right. So no wonder they say two can keep warm, right? Two can keep warm. Two are better than one. So if you are in bed with two people are in bed, they are likely to keep warm because they will be transferring heat energy. If one is feeling cold, the other one will transfer some heat energy to them. So heat is the energy which is transferred. Okay, this is arbitrarily, but in a sense, just for first year physics, let us just understand that heat energy, it is that which is transferred, that energy which is transferred from a warm body to a cold body. And it is usually due to the difference in temperature. All right. So warmth will be talked about having a higher temperature than coldness. So from a warm body to a cold body, what is transferred is heat energy. All right. So the other aspect that I would like to just talk about in terms of heat energy is what it does to the molecule or the atoms of that substance where heat is introduced to. Okay, Precious, good to have you. How are you? Hello, Precious, how are you?
I'm fine, and how are you?
Awesome, awesome. How have you been? How was your day?
My day was just okay. Yeah, how was yours?
Yeah, it was fantastic. Yeah, though I went in town, so I came back a little bit tired. But anyway, good to have you in our class today.
Thank you.
Awesome. So we are going to just hint on what we are talking about when we say heat energy. So we are going to hint to just give a hint on what happens to the energy when it is transferred to a molecule. All right. Suppose you have a container. All right. For example, it's a gas, and then you get a torch. All right. You put, to that gas. What will happen to the molecules in the gas? What will happen to the molecules, especially in a gas, is that the molecules in a gas will start moving will gain some kinetic energy. All right, they will gain some kinetic energy. In this case, let's first look at the translational kinetic energy or tangential kinetic energy, which is just given by 1/2 mv squared. So this equation tells us that if we have a molecule or an atom with a mass, m0, traveling at a velocity, we can actually affect the motion of the atoms. How many of you know that atoms in matter are always moving, or molecules in matter are always moving? They don't stay in one position. They are either vibrating or translating from one point to another. How many of you guys know that matter is not going to sit in that position like that? The molecules, not necessarily the whole body, but the molecules. How many of you guys know that the molecules or the atoms in matter are always in constant motion? How many of you guys know that? Okay, Tekla knows.
Me.
Okay, Tekla knows that. Precious knows that. Okay, good. Kalma, good to have you. Though you have come in late, good to have you.
Thank you.
How are you?
I'm okay, thank you. How are you?
I'm fine as well. Awesome. Hope you can be able to just join where you can manage to join. But we are talking about thermal properties of matter, and we are firstly just talking about heat energy. And I was just talking to your friends about how heat is introduced. When heat is introduced to a molecule or a substance, what happens to the atoms or the molecules of that substance? Now, with this equation that we have here, 1/2 mv squared, this is translational kinetic energy. It is actually equated to 3/2 times K being just like constant, times T. So what this equation tells us that is that when I start to increase my temperature, what will change here on the left side? Anyone to help us? If I start increasing my temperature, what will change on the left side of the equation? Here on the left side. Here on the left side, what will happen? What will change?
I think the velocity of the gas molecules will increase.
Awesome. So, and this is more like the kinetic theory of gases. Also, yeah, what happens when we increase the temperature is the velocity will increase. So this is science that you need to know. You need to know that if I have my gas and there is heat introduced to that, what is just happening to my gas is that the molecules in that gas are just moving faster. And I can detect that as heat. If I touch an object where the molecules inside are moving fast, I'll feel that object to be warm. All right, so there's nothing special to warmth other than that the molecules in that warm material are just probably vibrating or moving faster. For now, let us try and just establish that. So when someone tells you, hey, this water is cold, is very hot, you tell them that the reason why this water is very hot is probably because the molecules in that water are vibrating or moving faster than usual. So for us, we can't see the molecules, how they are moving, vibrating fast, but when you touch, you can feel that warmth, and then you'll be able to detect, oh, the warmth is probably due to fast movement of, kinetic energy that is increased in that molecule. So what happens when, for example, let's talk for an instance, an air condition, all right, an air condition. So an air condition will supply some, for example, let's say in this temperature here, it's the temperature of the air conditioner, and this is the temperature of the room. So we have separated them like that, all right? So we have temperature of the air condition, temperature of the room, like that. And here we have brought them together in contact with each other. So as the air conditioner tries to blow in some cold air in the room, the warm air in the room will also try and interact with the cold air, all right? So That is why when you are standing just near a hot air condition, it will be much, much colder than when you go at a distance. Because when you go at a distance where the molecules, the cold atoms, the cold gas and the warm gas are interacting properly, you will find that the warmer gas of the room will have a higher kinetic energy and will collide with the cold gas from the air condition. And that collision, that transfer in energy will cause, just like the aspect of momentum, momentum, right? So the collision with the warm gas and the cold gas colliding will deliver energy, will distribute energy among each other due to momentum. So the one that had no energy will be given some energy by the other one due to collision and the like. But what you discover is that in that way, while the collision is taking place, it is actually bringing about a uniform temperature. And that uniform temperature will be in the middle. So let me just give another analogy. You have hot tea and you have some cold water. All right, maybe cold water is about 10 degrees, but hot tea is about 100 degrees. When you get that cold water and put in the hot tea to try and maybe reduce the temperature, that temperature will be in the middle between the cold area, this T1, the cold area, and the hot area. So it will be greater than the colder temperature, but less than the warmer temperature. That will be our final temperature because due to exchange of energy by collision. That is in terms of gases mostly. But when we go to more complex situation, all right, more complex situation where we talk about thermal energy, all right. So when we talk about thermal energy is when we introduce heat. For example, how do we introduce heat to a substance? Maybe let me just give this one as a question as well. I hope you are following. I've also taken note. Mr. Gilbert also followed us earlier on. I hope, Mr. Gilbert, you are well. In fact, how are you, Mr. Gilbert?
I'm fine. How are you, sir?
Awesome. I'm fine as well. So, yeah, we're just having an introduction of the topic, thermal properties of matter. And yeah, we're just discussing about heat energy, but now we want to talk about thermal energy. All right, before we talk about thermal energy, let me ask one question. All right, if you have, let me just talk about, for example, water or any object. How do you think you can, increase the temperature, or how can you introduce heat energy to a substance? In what ways can we introduce heat energy to a substance? Someone to give us answer? In what ways can we introduce heat energy to a substance? Okay, let's go. Kauma, in what ways do you think we can introduce, how can we introduce heat energy to a substance?
I think by placing it in thermal contact with another substance that has higher energy.
Higher energy? What type of energy? Is it?
Higher heat energy.
Okay, thermal contact. Okay, awesome. That's a good one. Let's go. Precious, how can we introduce heat energy to a substance?
How about in this case whereby you heat something using fire?
Okay, heating something using fire. Awesome. That's a good one. Let's go. Sante, how can we introduce heat energy to a substance? Scientifically speaking, you guys are scientists. Sante, are you there? Okay, so it seems Sante is not available right now, but Sante, I think you are available. I can see you. Are you with us, Sante?
What?
You were sleeping.
I was
Yeah,
changing the. Anyway, it's okay. At what?
yeah, I was saying how I was asking your friends and they are responding. I'm asking you guys that how can we introduce heat energy to a substance? Heat energy. How can we introduce heat energy?
By providing a heat source. That's just my thoughts. Providing a heat source, I guess.
Yeah, where
Something
is
that can
it?
produce heat.
And what give us an example? Because that is, you have more like rephrased the question. You have rephrased the question. So the question is, how can we provide a heat source? That is my question actually. Where is the source?
How can we provide a heat source?
Where is the heat source? Where is it?
Or a source?
Where is it going to
Like
come
from
from?
fire and so on.
From what?
Like from fire.
What is
Like
fire?
maybe
What is fire?
again. Huh?
Yeah, you are a scientist.
So
Okay, so I would have loved to hear more all of your responses, but to be honest, I would like to challenge you guys to be scientific thinkers. Whenever you are giving a speech, they have called Kaoma to say, Kaoma, could you say something? You are a scientist. You have to use scientific terms. So when you use fire, describe it what it is scientifically. Of course, the layman knows fire, but the scientist should be able to tell us what fire is. So we'll be able to see down here what some of the sources of heat or how we can introduce heat to heat energy to a substance. But as I was just talking earlier on, I was saying that heat energy, or should I say, yes, heat energy is mostly or directly related to the kinetic energy of the kinetic energy of the atoms or molecules which have that heat energy. So what you will see is that when we look at monoatomic gases, all right, monoatomic gases, these are gases that you won't find helium written as He2, because helium is a monoatomic gas. It doesn't easily react with others. Boron and all those inert gases. All right, it has a valency. It has one orbital with 2 electrons which are already there. So it is different from hydrogen. So it is a monoatomic gas. So with a monoatomic gas, mostly when we talk about its kinetic energy, we are mostly talking about its translational, meaning moving from one point to another, translational kinetic energy, and not rotational. Remember, even atoms can be looked at as some small spheres, all right, that can easily rotate. But when we talk about monoatomic gases, we just talk about mostly their translational energy, and we neglect their angular, or should I say, rotational energy, rotational kinetic energy. So, but when we talk about diatomic, all right, this word, diatomic molecules like nitrogen, oxygen, which are a bit more complex and bigger, here we also attribute their largely to, we also talk about their, since they have large moment of inertia than monoatomic gases, we also put into consideration their rotational kinetic energy. All right. So you expect that if a hydrogen or an oxygen gas, if you introduce heat energy to that gas, the molecules in that gas will not only move translationally, but they will also rotate because they have that high moment of inertia. So we need to be able to take into consideration that. So one thing that you see with diatomic gases is that, for example, oxygen. So we have one atom of oxygen here and another atom of oxygen. Wherever this atom goes, this other one should also go. That's how they are. They are married like that, all right? Not where some married people, in these small marriages, which you are marrying yourselves, you find that the boyfriend or the girlfriend, they don't even sit together in church. Yeah? But these oxygen gases, they sit together everywhere. Not at these atoms, they sit together. So check your small marriages. Yeah, but in any case, the atomic structure that presents oxygen as a diatomic molecule also presents, the bond between these two molecules is more like, can be treated as a string, all right? Such that when these two molecules are bumping into other molecules and whatnot, these two molecules will be vibrating with relative to each other. They won't separate from each other because they are bound covalently. They are bound like that, but they'll be vibrating just. So you should also know that vibration is also a form of energy. So you will know that when you introduce heat to an atom or to an oxygen gas, it won't only rotate, but it will translate also, and it will also vibrate. So there are those considerations. There are also other molecules that are more complex, a bit more complex, where they have 4 atoms. Wherever this one hydrogen goes, this carbon should go, and they move like that. So you'll find that there will be now more complex things to be factored in. So there will be more to deal with. There will be more things to deal with: the vibration, the rotation, the kinetic energy. So this is what leads us to the other aspect now, which we are talking about as thermal energy. All right. So we are talking now about thermal energy because here the energy, when we add energy, heat energy to a substance, we expect it to vibrate, rotate, or translate. All right. And this happens in more complex molecules that are more like diatomic molecules or liquids and solids and like that. So it is more complex that way. So I'm giving you a feel of science in the ordinary things that we see. When you see a pot boiling, you just think about that this heat energy coming from the stove is introducing so much heat that these molecules in the water are gaining more kinetic energy, such an extent that they can even escape the surface tension. You know, the surface tension of a liquid. That what's this barrier or the surface tension can be ruptured, and the water molecules can actually even escape. Do you know the reason why we have water vapor coming out of water, when you're boiling, is because the heat from whatever source we are using has given the water so much kinetic energy such that they are free to even move away from the whole body and start living in air, in open air, and the water vapor will now become a gas, having more kinetic energy to move around from any place where they wish. So that is what happens actually when we are heating. Nothing special, but yes, that same thing is very special. So it's all about kinetic energy, whether rotation or vibration or whatnot. So now, let me ask, are we following, my friends? Maybe I'm just talking to myself. Are we following?
Yes, sir.
Yes.
Okay,
Yes.
awesome.
Yes.
So these things that I'm saying are mostly likely to come in your multiple choice questions. So just try and pay attention. If you don't pay attention, if you are just getting some jargon here and there, make sure you read this document. It's there on Moodle Physics, but I'll be able to prepare a more simpler one for the next other chapter, which will be talking about specific heat capacity. So here I just want to introduce just you guys for the love of science. So when we talk about these random, there's vibration, there's rotation, and there's translation. These things tend to be random. So the energy, all right, I'm here. The energy that is resident in this random motion is what is called thermal energy. All right. Heat energy was only concerned with the kinetic, only one, translational kinetic energy. But thermal energy now just looks at the whole picture, whether it is rotation, whether it is vibration and all that. So these random movements and random collisions and whatnot, these are just now what we talk about as thermal energy. So can we be able to differentiate between heat and energy and thermal energy? Are we able to differentiate heat energy? Mr. Gilbert, are we able to differentiate between heat energy and thermal energy?
Yes, sir.
All right, what is heat energy?
It's the energy due to the kinetic. It's the kinetic energy of particles.
Okay, heat energy. Oh, thermal
That's
energy.
heat energy.
Thermal energy.
Thermal energy, the energy due to the kinetic energy, translational, rotational, and also the vibration of particles.
Okay, that's a good one. Okay, though, when we talk about heat energy, all right, heat energy, it's not only kinetic energy, because even vibration is also some form of kinetic energy, even translational, but we have to specify translational. So kinetic energy is in different forms. There's rotational, there's vibration and whatnot. But in this case, let's specify as translational. Average, actually it is average. The reason why you saw this, for example, have you seen here, V, there's a bar on top of V. This bar is talking about average. So this is the average kinetic energy of that substance, all right? Substance is better to say. Substance or molecule, yeah, even atoms. So the average kinetic energy of a substance is called heat. But then when we talk about random motion in a substance, we talk about there. So here we are saying thermal energy is the energy associated with random, all right, random motion of the molecules. So that is what we call heat energy. All right. So heat energy is, not heat energy, thermal energy is the energy associated with random motion of atoms. All right. So when heat flows in a substance, it is often changed into thermal energy. So when I introduce heat, all right, by a heat source, we'll be very quickly, we'll see some form of heat sources, all right, so that even when we say fire, what do we mean? All right, fire. Another term for fire is combustion. Combustion. You discover that combustion is a chemical formula, which is an exotic what? It should be, yeah, if I've not forgotten my chemistry, should be an exotic reaction or so. There's no.
Exothermic.
Thank you. You know, it has been when you were in grade 1, that's when I did my first year. So, you know, it has been a long time. Exothermic. So that is combustion, and that is what we mean by fire. So a scientist shouldn't just say fire. They should say an exothermic reaction can produce heat energy. So before we go any further, I just want you guys to just note this clearly, that when we talk about thermal energy, we talk about the energy that is associated with random motion of molecules. All right. So I think this is now the time that I just need to tell you some of the sources of heat. All right, sources of heat. So sources of heat is friction. Friction. Do this experiment. All right, get cold water and get a metal and start steering in that water very fast. You steer. What is likely to happen is that it is possible that you will raise the temperature of that water. When you touch it, you start feeling a bit cold. But I'm yet to verify that. I've also not experimented it, but it's supposed to happen. But what is also there is that just get your own hand and another hand, start rubbing in your hands like that. I don't know if you are able to feel something right there. You feel warm. You have generated heat energy by moving across, the surface atoms or surface molecules in your hands. You are introducing kinetic energy to them as you are rubbing against your hands. So what will happen is you will start rubbing against them and they will start gaining some kinetic energy, and then they will eventually, you will feel warm that way. All right. So that is how we can introduce it through friction. All right. We can introduce it through combustion, which is so-called as fire. All right. Which is an exothermic reaction. All right. So I'm opening your mind now. So how else now can we introduce heat? All right. So also infrared radiation move with heat energy. All right. That's why the sun, you can feel that it's hot because of those. In fact, the sun comes with ultraviolet radiation, but hot objects also emit infrared radiation, and that infrared can carry heat energy. All right. So we have so many sources of heat energy, and also other, how the sun produces. Who knows how the sun produces energy? Why is it that the sun is hot? Who gave the sun heat to be hot? Kaoma. Who gave the sun heat?
Chemical reactions take place in the sun.
What chemical?
That emit, I think, fusion, something like that. I'm not so sure. I've forgotten.
There are different reactions. You said what?
Something like a fusion.
A fusion.
Yes.
Awesome. I like that you are near. Fusion, chemical fusion. It's not a chemical reaction. It is actually chemical fusion. So it's different from chemical reaction. So this is where just, helium turns into hydrogen, and hydrogen turns into helium, and helium turns into hydrogen. And as fusion is just two, for example, two atoms of hydrogen turning into something like that. Two atoms coming together, they form a bond, and then when they separate, something like that. So it's chemical fusion, not necessarily a chemical reaction. So that continuously happens, and it emits that energy that we feel even here, traveling as an electromagnetic radiation. So I just want you guys to love the science such that you can even go on YouTube and just spend time even if it's not school related, just watch some science stuff. All right. I didn't know all my science from school. No lecturer taught me some of the things I teach you. So it's just whereby just falling in love with the science and just reading more, exposing yourself more. You are now scientists, natural scientists. So anyway, time has not allowed me. We can end here for today because it was just an introduction. If you have any questions, please, you can send the questions in the group because Zoom is telling me that time has gone out. But otherwise, it was good to have a class this afternoon. Have a good afternoon.
Good afternoon too.
Awesome.
Thank you, sir.
Awesome.